All right, so here we have a heat equation where this is the heat equation, 2 is the constant K. If I draw the picture, it's like this width of the rod is 5, this length is 5, and on the and it's surrounded by insulation, so it doesn't lose heat on the other sides in the radial direction. But on the left side is touching ice. On the right side, it's touching something here, but it's like it's touching the boiling water. So you have some boiling water here and then some metal here. So we'll assume that this is always kept at 100 degrees Celsius, and this is always kept at 0 degrees Celsius. Okay. And then before this, the ice was touching this, and before this boiling water was touching the right side, we are going to assume that initially the temperature across the rod was 0, just because it's easier that way. Okay, so it was like very icy, very cold in the beginning, and then you can kind of imagine what the solutions might look like. The solutions will look like initially it will be like 0, but then because the right side is being heated, this is going to go up, right? But it's going to go up like that. Right? So if this is 100, then when this does reach 100, then it's going to, the left side is kept at 0, this is kept at 100, so at some point it will just get closer and closer to this straight line. And that's what's going to happen, right? Okay? All right, so how do we solve this? Well, so you start to think about this solution right here. So that's a stabilized solution, right? So if you send time t to infinity, then the system becomes stabilized, and you end up with a temperature distribution that looks like a straight line, right? So here's 5, here's 0. And that line itself should be a solution that satisfies the heat equation as well, right? So, because I mean, if the initial temperature distribution was like this, and you got all these conditions, then you'll always be like this. It wouldn't change. So we know that this is a solution. So we start from there. We start out by saying, what's the equation of that? Well, this is x, and this is the u, right? So, and this is a straight line. And I know how to get equation of a straight line. What's the equation of a straight line?
mx plus b.
Yeah, and then it's y equals to mx plus b. Instead of y, you have to say u. U is mx plus b, and then y-intercept is 0, so b is 0. And how do you get the slope?
Divide 100 by 5.
Yeah, divide 100 by 5, so it's 20x, right? So we have this solution 20x, and although I want solutions to be a function of x and t, I'm claiming that this solution 20x will satisfy these two conditions, not the initial condition, but just these two, the heat equation and the boundary conditions. Right? So to check whether this satisfies the heat equation, so claim this satisfies heat equation plus the boundary conditions. Right? remember this one's called boundary conditions. This one's called the initial condition. This one's called the heat equation. So the first two equations are satisfied. And this one's, the boundary condition is extremely easy to check, right? If you plug in x equal to 0, what do you get? 20 times 0, that's 0, right? If you plug in 5, 20 times 5, that's 100. So it satisfies the boundary condition. Check, okay? Slightly non-trivial would be this one, so let's try to calculate this. ut is what? Ut means you differentiate u by t. It's a partial derivative. So x is considered as a constant, right? So what do you get if you do ut?
0.
0. Okay. What about uxx? Well, ux would be just 20 because you differentiate this once by x. But then if you differentiate this again by x, what do you get?
0.
0. So the left side is 0, the right side is 2 times 0, so it's checked. So it satisfies the heat equation, satisfies the boundary conditions. Which, by the way, of course, we knew it was true, right? If you have a straight line, it will be a solution that doesn't depend on time. Okay? Once you reach this straight line, then there is no heat change. The temperature will stay like that because, I mean, it should be like that, right? Okay. Any initial condition will converge to this straight line as the solution at time infinity. So that's what we know. Okay. However, this is no good because there's no way you can make this initial condition to work, right? So we use the following idea. So in the non-homogeneous differential equation, so suppose you have like y double prime minus 5y prime plus 4y equals to, say, e to the 10x. Right? What do? You find a solution that satisfies y complementary will be a solution that satisfies this equal to 0, right? And you have another solution, y particular, and you just find one solution that satisfies the other one, right? And you said like a times e to the 10x. That's the method of undetermined coefficient. You plug that in and see which value of a would make this equal. And once you have it, you add the two. Right? Now, it's not exactly like this, but it's almost the same idea. What we're going to say is that we're going to just put a number here and say u1 is 20x and u1t, u1x, just that. Okay. And then define v xt as u xt minus u1 xt. Now, uxt satisfies all of the conditions, so specifically it satisfies these two. And u1xt satisfies these two. Therefore, if you subtract it, it's going to satisfy this one and this one, but this will change. So let's just see what that is. Okay. So first of all, vxt satisfies the heat equation. That's because heat equation is linear. So if these separately satisfy the heat equation, if this equation satisfies separately, then adding them or subtracting them will make it satisfy. So V is the difference of the two solutions, so it will again be a solution to the heat equation. Now if you don't believe me, you can actually put it in here. So if I differentiate this by t, then they're separately equal to 2 times uxx and 2 times u1xx. So that's same as, just try it, it just works, okay? All right, however, the thing is, V0t is U0t minus U10t. What's that? Yeah. So I know that U10, this thing here, satisfies 0 and 100. And because it specifically is 0, right? So this is 0. And U is something that satisfies this, so it's 0. So it's 0 minus 0, which is 0. Now, V of 0t, 5t, is U 5t minus U1 5t. What's that? U5t is 100. U1 5t is 20. You plug in 5 here. 20 times 5. 100. So 0. Okay? Okay, that's interesting. Okay. Now, Vx0 would be what? Ux0 minus U1x0. This is a nice question to ask. No, it's not 0 minus 0. The problem is U1 only satisfies the first two. It doesn't satisfy this. So what would it satisfy? Okay, 0 minus what? Okay, I would give you the answer, but this is such a nice question to ask. I want you to think about it. Think about what U1xt is. What would you get if you evaluate U1x0? Yeah?
Would you just get 20x?
Yes! This is U1xt, right? You plug in t equals to 0. It doesn't depend on t, so it's just 20x. So you get negative 20x. Okay, now see what we have transformed the equation into. So for v, we have vt equals to 2 vxx. v0t equals to v5t equals to 0. And vx0 is negative 20x. Okay. Now, isn't this exactly the kind of question that we solved yesterday, right? It's the differential equation where the endpoints are 0, right? The endpoints are 0, and you have some initial condition. This is like initially you have a bar where it's like negative 100 degrees on the left side, very cold, and 0 degrees on the right side, and now it's touching ice. Even if it's touching ice, this side is going to go up in temperature. Right? That's what's going to happen. Right? Which is certainly solvable by using exact methods that we used. Now, we could go on to solve this, but let's stop for a moment and see what we should do after we get it. Once we get the V, how do you recover U? You know what this is, right? This is a 20x, right? So you just move it there, and uxt would be whatever solution you get from here, and add 20x and you're done. Right? Okay, so it works. Okay. Now, again, when you solve differential equations, a lot of times you feel like you're just making guesses and just trying things out and see if it works or not. But always our mantra is that we're not really solving differential equations. We always construct some solutions, see if it works, and if it works, then the mathematical theorem of existence and uniqueness just helps us out and say that that's the solution that we were looking for to begin with, right? Okay, so if you're convinced, we are going to just write down the following and move on. So we will just say that u xt at the end of the day will be vx, well, I'll just put 20x plus vxt. Because u1xt is 20x, so if you move it to this side, you get 20x plus vxt as uxt. So that's what we're going to do. Okay, so this is a good time to review what we learned yesterday. So what's the step one? How do you solve this? What do you do?
Look for all solutions of the heat equation.
Huh?
Look for all solutions of the heat equation.
And the heat equation and?
Plus the boundary condition.
Plus the boundary condition. In what form?
U of xt is equal to x of x times t of t.
Yeah. And that's called the separation of variables, right? You imagine that the solution looks like a function of x times function of t. You plug it into the heat equation, which gives you x of x times t prime of t equals to 2 times x double prime of x times t of t. That's because on the left side you're differentiating only by t, so only this t function gets differentiated. On the right side you're only differentiating by x twice, so only the x function gets differentiated twice. And then I want to stress this next step because a lot of times people forget. You always want to divide by 2xt. Okay? This number times the x and t, the original function. Okay? And the result of that is x over x will cancel, so you're going to get t prime of t over 2t of t. This is really x of x and t of t, and I just didn't write down. Sometimes I just don't write them down. And then the 2 will cancel, t will cancel, so on the right side you're only going to get x of x over x of x after dividing by that and simplifying. Okay, now what's our argument?
That the two functions need to be constant.
Right, because the left side only depends on t and the right side only depends on x. If a function of t is equal to a function of x, they can only happen if both are constant functions. Right? If they change with respect to x or with respect to t, there's no way that the two sides are equal for all values of x and t, because equal sign in differential equation means equal as functions. Okay, so function of t and function of x can only be equal if they are both constant functions. And what did we decide to name this function as?
Negative lambda.
Negative lambda. Very good. Yeah. We name it like this. And then this splits into two equations. This first one gives you t prime equals to 2, actually minus 2 lambda t. Again, I'm not writing down t of t, forgive me. And then if I move this to the other side and bring it this way, add lambda x both sides, then I get x double prime plus lambda x equals to 0. Okay? So we're trying to solve this equation, and we worked with the, oh, I shouldn't have said u of xt, it's really v of xt. Sorry about that. So we're really trying to solve this, right? Okay. Now, v of 0 t is x of 0 of t, and for this to be 0, we must have x of 0 as 0. Let me check. Why not t of t equals to 0? What goes wrong if t of t is 0?
That it's trivial.
It becomes trivial. T of t, if that's 0, then v just becomes a trivial solution, and that's not, those are not what we want. So we have that, and then similarly, v of 5t equals to x of 5 times t of t equals to 0. So that would mean that x of 5 equals to 0. And then that gives you the Sturm-Liouville problem. So combined with this and these two endpoint conditions, you're going to get the Sturm-Liouville problem. And okay, let me be really concise and quick about this one, but hopefully you can figure out yourself as well. So you're doing x double prime plus lambda x equals to 0, so that r squared plus lambda equals to 0, so that r is plus minus square root of lambda I. And therefore, your x must be c1 times cosine square lambda x plus c2 times sine square lambda x. And then if you apply the condition that x of 0 is 0, this has to be 0, right? X of 0, for this to be 0, this term, this c1 better be 0. If c1 is non-zero, there's no way you can get x of 0 is 0. So you know for first hand it must be this one. And then for this to be non-trivial and still satisfy x of 5 equals to 0. Let's see, what's x of 5?
0.
I mean, it's 0, right? So, but if I plug it in here, it's c2 times sine square root lambda times x times 5 here. And since c2 cannot be 0, c2 0 means that x becomes trivial. We don't want that, so it has to be sine being 0. For the sine to be 0, we better have this thing inside the sine to be n pi. So we end up with square root of lambda times 5 equals to n pi. Divide by 5 both sides. And you get square root of lambda equals to n pi over 5. And specifically that lambda must be n squared pi squared over 25. So we got almost everything. So we know that the eigenfunctions are sine square lambda x with square root of lambda being n pi over 5. So with that, we get the following. X of, what is it? X of x must equal to sine of n pi over 5x. Now there's still a step that I skipped. You also have to think about what happens when lambda is 0. Okay? But that you should work out. If lambda is 0, you end up with x being a plus bx. And the two conditions forces both a and b to be 0. So for lambda equal to 0 case, you don't get a non-trivial solution. So the only way that you can get a non-trivial solution to these three conditions, this equation and these two boundary conditions, is if the function is some multiple of sine n pi over 5 times x. Okay? So that's our x of x. And then we put in the value of lambda here. So that's the second equation for t. So t prime is negative 2 times n squared pi squared over 25 times capital T. And we know that these kind of equations always have the solution as t equals to e to the negative 2 over 25 n squared pi squared, t as the solution, or some constant in front. This also has a constant too, but if this is c and this is c2, then you can just rewrite the c1 times c2 as another c. So at the end of the day, your conclusion is that v of xt must look like some constant times e to the negative 2 over 25 n squared pi squared t times sine of n pi over 5 x. And then you start thinking, okay, so this is a solution for every n, but then if you add these solutions for different n's, it will still satisfy the first two conditions. So you just add them up, and because these coefficients can be different, you just put Cn, n from 1 through infinity. So that gives you the general solution for the first two, and now you just have to apply the initial condition to figure out what the solution is, okay? And then the next step is, so that's step one, and then step two, you have to use Fourier series. In this case, if you plug in t equals to 0, you end up with a sine series. So step two, you have to figure out the Fourier sine series of series of 20x, right? At negative 20x. So let's try that. Okay, so negative 20x. So the formula for Bn in Fourier series is 2 over L integral from 0 to L f of x sine n pi over L x dx. Okay, in this question, what's our L?
What?
5, because that's the number in the denominator of n pi, so this is 5. So in our case, it will be Bn equals to 2 over 5 of 0 to 5. And what's our function? What are we trying to get the Fourier series of? Negative 20x, this one, right? So put negative 20x sine n pi over 5 x dx. And let's move this outside. So 20 divided by 5 is 4. 4 times 2 is 8. So you get negative 8 times 0, 5 x sine n pi over 5x dx. And we can use the tabular integration. X differentiates to 1, 1 differentiates to 0. Sine n pi over 5 integrates to negative cosine with 5 over n pi appearing every time you integrate. The reciprocal of this number will appear in front. And then integrate again, another 5 over n pi will come out, so you get 5 squared n squared pi squared sine n pi over 5. And this alternates, the first column alternates, and then you get the results by doing this multiplication. So we know that the integral is negative 8 times negative 5 over n pi cosine n pi over 5x. And then negative times negative positive, so it's plus 25 over n squared pi squared sine n pi over 5x. And then you have to plug in 1 and 5 and 0. Now you can check that in both cases when 5 and 0 goes into sine, when 5 goes in here, sine of n pi over 5 times 5, they cancel, so you get sine n pi, which is 0. And when you plug in 0, what's sine 0? 0. So that doesn't produce anything for each of these cases. This one, I guess I can multiply negative 8 inside to get 40 over n pi. Or I can pull this out. So it's 40 over n pi. And then when you plug in 5, what do you get?
Negative 1 to the nth power.
Negative 1 to the nth power, right? And then when you plug in 0, what do you get?
Negative 5 over n pi.
It's just 1, right? Oh, sorry. I messed up here. I forgot this x. I knew something was wrong. So when 5 is plugged in, this is really negative 1 times 5. And then when you plug in 0, that doesn't give you anything. Is that good? When you plug in 0, this 0 makes it 0. So this is the only thing that you get. And 5 times 40 is 200 over n pi. negative 1 to the nth power. And that means that the result of this calculation, if you look at the Fourier sine series formula, it says that negative 20x is same as summation of n from 1 through infinity of 200 over n pi, negative 1 to the nth power sine n pi over 5x. And we also know that if you plug in t equals to 0, Vx0 is negative 20x. And that's why we tried to get the Fourier sine series of negative 20x. You have a question?
We need to include the e to the negative 2 n squared pi squared over
So I'm getting there. Okay, so if I plug in t equals to 0, this disappears. And I know that this left side is negative 20x equals to this right side. And that form looks exactly like this one, where instead of Cn you have this. So you know that Cn's are actually same as Bn's. I'm making this argument because soon we are also going to do the case when the boundaries are insulated. In those cases, the Cn's and the Fourier coefficients don't directly match, so you have to do a little bit more work. Here, when you have the endpoints fixed to 0, then Cn's and the Bn's are exactly the same. Okay? So that just happens to be that one. And therefore, we can write down the full answer. Since I figured out what Cn's are, we can write down the full answer for Vxt. So what did we get for Vxt? The answer for Vxt is n from 1 through infinity. What do you do? This is the Cn, right? Plug in the Cn. Oh, I forgot the e. Shouldn't forget that e to the negative 2n squared pi squared over 25t sine n pi over 5x. Okay, however, this is not the answer yet. What's the answer to the original question? What's the answer to the original question? What do you do? We want u, not v, right? So what's the answer to the original question?
I'll need to add 20x.
Yes. You have to add 20x. So you have to say uxt is 20x plus vxt. So remember that was our plan, right? So let me write down the answer here then. 'Cause I still want to say a few more things after that, okay? Okay, so the final answer, after so much calculation, is that uxt must equal to 20x plus summation of n from 1 through infinity of 200 over n pi, negative 1 to the nth power, e to the negative 2 over 2n squared pi squared over 25 t times sine n pi over 5 x. That's what it is. And I still want to say something about this. So that's the answer, but I still want to say something about this because there's something called, so question 2. What is the temperature distribution after a long time? Okay. And then you answer that by taking the limit of this uxt where time t is sent to infinity. Okay? So time, you just send time to infinity, right? Then what happens is that 20x doesn't have any time dependence, so 20x just stays as it is. But then if you can switch the limit with this infinite sum, what's happening is that you get the limit of t going to infinity of this thing inside. So look at where the time dependence is. Only this is dependent on t, right? So you have t right here. So you have e to the negative some large value because you're sending t to infinity. What is e to the negative infinity?
0.
So what's going to happen to this term?
You're going to use it to 0.
You're just adding up zeros, right? So you get zeros, and therefore the final answer is this 20x. And that's exactly in accordance with our initial intuition that the right side will start rising, and after infinite time you're going to end up with this straight line whose equation is 20x. Okay? So that's what we have. Now I want to show you what the picture looks like if I try that. I don't know if I can. So let's see. All right, so I'll use Python to draw that thing. So I'm going to define uxt by the function that we just did. So initially, I'll make the y value to be, sorry, not uxt, ut. The y values, I want it to be 20 times x, because that's the beginning. And then for n in range, I'll just add up 100 terms. I'll truncate that summation after 100 terms. And you're adding, what is it, 200 times, let me define pi, because I'm using that a lot. Pi is equal to 8.1415992. So we take 200 divided by n times pi times -1 to the nth power. And then times exponential function with -2 times n squared times pi squared times t divided by 25 times sine of n times pi times x divided by 5, right? And then we'll return y. Okay. All right, and we'll just plot this thing. I did that before, so we'll choose this one. Because I made the k as 2, this is going to probably go really fast. I'll just first 10 seconds. Let's see what happens. Oh, I have to delete the previous graph. Okay, let's see what I get. Oh, okay. Already at time 1, you get something like this. So let's do this. Let's do t in a range, and I'll put from 0 to, no, I'll just do lin space. Lin space. The first maybe 2 seconds, and I'm going to divide that by 11 different places. So the pace is like 0.2 seconds. No, I don't like that either. Let me just look at the first 1 second, okay? So first 1 second. Okay, so here's what's happening. Sorry. There's another problem. I have to redefine my x. X equals to lin space. because I was using this for some previous thing. 0, 5, 101 points. Okay. All right, now we get this. Okay, so when it's 0, it's supposed to be 0 everywhere, but there's this Gibbs phenomena because we have this jump discontinuity from 0 to 1. But anyways, you see what's happening? We get, after time t equal to 0.1 seconds, you get this line, and it keeps going up, right? And if you send t to infinity, if you plot x with u of 10 seconds later, you're going to end up with a almost straight line, because everything just, it's like after a long time, this should be the heat distribution. So that's what we get from today's calculation.